And then, okay, so far we have talked about the theory. We could talk about the detectors and accelerations. Now there goes to the major part, the WZ analysis. All right, here the left schematic diagram is the analysis scheme. Above the red dashed line is not done by me. It's done by some experts in CERN, maybe in US, I don't know. They just these are the experts doing the simulation, the generation, the digitization. They prepare the data. That's what we call the reconstruction data. But to my point of view, it's still raw data for me because there's just a basic physics objects there. So one of my job is to do the selection and to do my interested physics topics. So based on the reconstruction data, just right below the red dash line, I first did the pre-selection. This pre-selection is where loose cut criteria. Why we want to do this? Because first, number one reason is we want to reduce the data size. We want to reduce those garbages which has nothing to do with my analysis. So I just want to reduce the data size to copy it back to do my analysis more effectively. So then another reason is we want to prepare for the two completely different methods for analysis. So these are straight cuts. Normally we talk about is the tightened straight cuts compared to the very loose cut criteria of pre-selection. And another one is a relatively new method. It's called the boosted decision trees. It's a multivariate method. So here I list the table is about the data set we use. All these data are simulated data. They are not real data. And they are generated in different channels for all the background and signals. If you look at the middle of the table, you see the Z plus jet. They got four different energy regions. They generated in separate energy regions. I have asked some guys why they want to do this because it just increase your times. So they told me that it's because if you look at the second column is the cross section of this one. You see the cross section very large, very huge between different energy regions. So that means if you just generate the Z jet in a whole energy region, most of the sample the ones will fall into the very low region energy region because they have bigger cross sections. So that's not fair. That's not for those regions which has very small cross sections. They will not have enough statistics. So that's not good. So they divided these energy into different regions and then generated them separately. So that's just a technical thing. And the signal and the background data size, it looks enough. And here we do the pre-selection. Okay, the pre-selection criteria I listed here. It's on lepton. It's only on lepton, and the total number of leptons have to be 2 because my signal is 3 lepton final state. So that's pretty reasonable. The missing ET relatively low energy. The Z and the W boson is a relatively wide mass window. So the bottom two plots shows you the PD of leptons from Z and the PD of leptons from W. Maybe someone already noticed that some of the background even they don't have Z, they don't have W. So how it makes sense for these, let's say TD bar, the PD of leptons from Z. Because here, that's the definition we use, and also the mechanicism. The TD bar will fake to our signal. If the pair of leptons decayed from TD bar, their mass energy falls into the mass window of Z. We see that those leptons pairs fake Z. So that's how we define Z here, and the same rules applied to W. And the more plots, it just shows you the different distributions, the different behaviors between signal and background, and some of them is signal and background, they are separated very clear, but some of them they are not. If you look at the bottom right, Z, the environment of Z, you see that only TD bar they got relatively flat region, and the others they all have Z peak. Because if you look at the channels, you see that Z jet, ZZ, Zhuoyan, there is a real Z there. So there's nothing to do to separate them based on the environment of Z, because they have a Z there. So that's why we want to choose a lot of criteria to separate our signals between the background, because the signal is so sensitive. And all these plots are normalized to 1 inverse Fintel bar. Alright, more plots. It's the key plots. It's the PD of WZ, the environment of WZ. You see the bottom two plots are the scalar sum and vector sum. It's all criteria we selected for our pre-selections. And here the table shows you the pre-selection. After the pre-selection, the signal and the background, the selection efficiencies. And for signals, they are 25% and 29% respectively for W minus D and W plus D. And for background, most of the background has been removed, except for ZZ. And then we apply the Tetton straight cut. Here, Tetton straight cut is some kind of a some kind of a tight criteria based on the pre-selection. I didn't list the detail here. You can find it in my master's thesis. Here is the two tables. I listed Tetton straight cuts results after Tetton straight cut. The signal efficiency is about 8% and 7% respectively. And if I normalize to 1 inverse Fintel bar, finally I got 53 signals and 8 background. The S over B is about 6. Alright, the background contributions here, most of the background goes to the Z-jet, ZZ, and the Zhuoyan. It's pretty reasonable. And here are the 4 key plots. Here the red region is the WZ signal, and the other colors are the background. You see our selection criteria is very effective. And based on the Tetton straight cut, we do the WZ cross-section measurement, and also I analyze the statistical uncertainties and the systematic uncertainties. Here, the systematic I coded from Tevatron. I didn't analyze it because I don't have data. Normally, the systematic error is calculated from real data, so I just coded from Tevatron. Since the LHC is more powerful than Tevatron, so you will foresee that the systematic error will be much lower in LHC than in Tevatron. So here the numbers are pretty safe to put here. The luminosity is about 6% and acceptance is about 3. These numbers are pretty conservative. And based on these statistical and systematic errors, analyze all 4 channels, the uncertainties, and combine them together. Finally, we got 19% of precision for WZ cross-section measurement. If you still remember the D0 and the Tevatron results, this result is much better.